All right, so let's do day, what is it, 8? Day 8 of Advent of Code. Yes. All right. So let's see. Line no, yes. New Speckle J day 8. I think it is day 8. Yes. Okay. So I'm going to create a new project. It's a Clojure project, and it's using the testing framework Speckle J. All right, that's good. It created it. Now let's go to IntelliJ. And we'll get rid of day 7 here. Let's do a new project from existing sources. And it's going to be day 8. So let's go find day 8. Good, there it is. And we'll just select the project.cloj file that was created by that line again task. Yes, day 8, good. Yes, that's fine. Oh, let's have 1.8, shall we? 1.8, good. And yes, that's fine. Lovely. And okay. And let's see, there's the spec and there's the source. Oh, thanks for the tip of the day. And now we should be able to run this. It's got a little bit of a test code in it. So let's go to the line again task and create ourselves a line again task spec dash A, and that'll make it an auto test. So let's name this auto. All right, good. And now we should be able to run that. And dum da da dum. Good. Excellent. Good. We have everything running the way it's supposed to. Let's bring up the spec file. Let's move this like so. Let's go to the windows and bring up the split vertical tab. There we go. All right, now let's bring up the primary code. So we got code over here. We got tests over there. Isn't that nice? Okay, and we don't need any of that. So we're going to get rid of that code, and we're going to get rid of that code. Lovely. Okay. What is the problem that we're trying to solve? Well, let me show you the problem that we are going to solve. Oh, yes, this is a good one. Oh, yes. Oh, yes. Okay. All right. Never mind all this description. The input file is going to be this lovely little assembly language here. Now, it's a very simple assembly language. It only has 3 instructions. There's the no-op instruction that does nothing. And I don't think the argument to the no-op instruction is meaningful in the slightest. Then there's the ACK function, which just adds the argument to the accumulator. The accumulator is a register somewhere in the machine, which we presume will start at 0. And then there's the jump instruction, which jumps relative to its location. So this jump instruction would jump 1, 2, 3, 4 down here. And this jump instruction would jump -4, 1, 2, 3, 4, that way. So that's how that's going to work. And the task at hand is to take the input, which is here. Look at that. Okay, I've written code that looks like this. And find out which instruction is executed for the second time. Now, you may notice that this language has no decisions, which means if an instruction is executed for the second time, we have an infinite loop. Let's get this data here. We'll get this lovely program. Okay, and we're going to put it in our environment. We're going to create a new file. We will name that file input. Lovely. And we're going to just paste it right in there. Good. And now we have the input file. Okay, lovely. Well, okay, he said. So let's go back to our Advent of Code here thing, and let's just read the last little bit, right? Okay, immediately before, notice how they emphasized before, the program would run an instruction for a second time. The value in the accumulator is 5. Run your copy of the boot code immediately before any instruction is executed a second time. What is the value of the accumulator, right? So, okay, we're going to have to keep track of which instructions were executed. And before an instruction gets executed for the second time, they want the value of the accumulator. One thing I want to know is, does the accumulator start at 0? ACK increases or decreases a single global value called the accumulator, right? Okay, accumulator starts at 0, it says right there. The accumulator starts at 0 after an ACK instruction is yeah, okay, fine. All right, and we also presume that the instruction begins at address 0. So the very first instruction to be executed will be the first instruction in the list. Okay, all right, so this is going to be fun. I'm going to put this back up here where I had it before, okay? And I'll keep reference to it. Meanwhile, let's go here. All right, well, let's write ourselves a test. There are 3 instructions. So let's write the tests for the instructions first. So describe the instructions. Good. Okay, and okay, it should execute a no-op. No-ops are awfully simple, aren't they? Okay, and let's see. What do we want to say here? Well, what is the state of the machine? The state of the machine is the accumulator and the program counter. The program counter is the address or the index of the instruction to be executed. So, here's what we're going to do. We're going to say should equal I know PC of machine. So that's going to be the state of the machine. And that should be 1. Okay. So the program counter of the machine should be a 1 after the execution of. So let's see. I'm going to need a machine. Let's get a machine here. Let machine be the program counter starting at 0 and the accumulator starting at 0. That's going to be our machine. Okay. And I think, I've got to get the braces in there correctly, don't I? Yes, all right. So there's the braces, good. And this let is, more braces there than I need. The let needs to go around everything. Okay, so let's see. Did I get the let around everything? No. Is that there? Yeah, all right. So let's do this. Okay, that parenthesis shouldn't be there. Oh, good heavens. All right, so that's good. That's good. Let's see. Yes, all right. Let's reformat that. Does not look like it reformatted properly. So what did I do wrong here? This let goes there. Why isn't that indented properly? And the reason it's not is that it's the it macro is told not to indent by itself. So that's fine. We'll just let that sit there like so. And there's something funny there. I don't know what that is. All right. By the way, this test ought to run already, and it ought to say, hey, I expected a 1 but got a 0. Good. That's exactly right. All right, so now I want to execute the no-op instruction. Okay. Let. Okay, let my machine be the no-op of the machine. Now, this machine here is that one, and this machine will be new. Then we're going to take that and put it around the should. So now this machine will be that machine. And let's just do this. Let's change the name of this to init machine. Yeah, the initial machine. Okay, fine. So we're going to take the initial machine and we're going to execute a no-op on it, and we'll get the new state of the machine, and then the new state of the machine should be PC equals 1. Okay, and of course there is no no-op instruction, so let's create a no-op instruction. And define no-op, which takes, well, it does take an argument, but there's no reason for it to, so I'm going to not let it take an argument. And, oh, gee, what are we going to do? Oh, it takes the machine, of course. Yeah, okay, machine. Takes the machine. Okay. And now, the only thing I'm going to do here is update the PC. So, update, let's see, yes, the machine, the PC within the machine, and increment it. Now, if I did that correctly, I think that test will pass. Test passes, lovely. That is the only function of the no-op instruction right there. Although we should test that it did not change the accumulator. So let's just make sure that that's true, which is should equal 0. The accumulator, which I think is ACC. Yes, okay. I think I'll change it to AC. That's a more standard abbreviation for accumulator. Machine, lovely, and that should also pass. It does, good, okay. Next instruction. This would be the next it, so we're going to go down here, lovely. All right, it should execute an ACC. Okay, all right. Fine. Let's see. We're going to do the same thing. There's something wrong here. Oh, int. That's what's wrong. Okay. Let machine be the ACK of +2 of the machine, of the init machine. All right, so that's the initial machine. And we're going to increment +2. Okay. Now, should equal 1 colon PC of machine, because the PC does get incremented by the accumulate function. Okay, and should equal 2 for the accumulator of the machine. Okay, good. Now let's go over here. So now let's define this accumulate instruction, which takes as its argument some argument and the machine. And this time we're going to destructure the machine, so it's going to be PC and, let's see, what is that? Keys colon PC colon AC. I think that's how you do that, isn't it? Yeah, I think that's how you do that. Or is it PCAC? Let's just give that a try. I think it's something like that. Let's just have it return let's have it return this. Colon ACAC colon PC. Okay, let's see what that does. And let's see. Let's see. Map literal must contain an even number of forms. Yeah. So. Oh yeah, you got to do this. Expected one got a 0. Good. Okay. Well, all right. Then what we should be able to do is say inc PC, which is correct. And that should increment the program counter. And then we want to see the accumulator get added to, and that's just simply going to be plus AC arg, and that should pass. Huh, lovely. Okay, so now the accumulate instruction passes. All right, let's do the next one, and the next one is the jump instruction. The jump instruction modifies the PC. Okay, here's the jump instruction. Let the machine be the jump of the plus. Oh, let's make it negative just for the. Ooh, no, not negative. Well, there's no reason why it can't be negative. Minus 3 of the init machine. Lovely. Okay. And now should equal 0, the accumulator. And should equal minus 3, the PC. Okay, and I think that's going to fail because we don't have a jump instruction. So let's go to the jump here. Define jump arg. And we'll do the same thing here. No, I don't think we will, actually. I think we'll just say machine, and then we'll say update machine colon PC plus arg. I believe that will work. And it does. Okay, fine. Lovely. Okay, we now have our execution environment. So next, next what we want is a way to execute a bunch of instructions and keep track of which instructions were executed. Okay, well, so we'll write ourselves a little test. And let's get a program, shall we? Okay, the program is going to be ooh, I'm tempted to do something ugly here, but I'm not going to do anything clever and ugly. The program is going to be this. It's going to be let's see, what's the best way to do this? Okay, yes, all right. Accumulate 1. There's one instruction. Jump 2, that will skip the next instruction. Make sure I put a little colon in front of that. That's going to be a jump. Good. Okay. That's going to be accumulate -1. And that'll be the end. Oh, no. A no-op. And the no-op has no argument. Or if it does, we don't care. Okay. Now, 2 things are going to happen here. I'm going to execute this program. So let's describe this differently. Well, I can do it in here. These were the instructions. So let me do this, and I'm going to describe execution. It should execute. Well, fine. Now I want this program not to be there. I don't want that to be there. So I think that's all I need there. Let's just do that. Okay, and we'll do another let here. All right, so let program be, oh, I think I've got that already. So yeah, let program be that. Okay. This parenthesis should go to the end of that. Good. Everybody aligns properly. Good. All right. All right. Let okay. Let the machine good be the execution of the program. Okay. That's nice. And let's destructure this. Like so. I believe that's how you do that. All right, and I think all this compiles and runs and everything. No, it doesn't. Unable to resolve symbol execute. Well, that makes perfect sense. Defin execute program. Lovely. And let's just have it return AC0 and PC0 just for the moment. And that should tell us something down here. Yes, everything worked properly because we don't have any shoulds. Okay, now let's put some shoulds in there. Should equal, what should the PC be? The PC should be 0, 1, 2, 3, 4. PC should be 4, but there is no 4. Right, so that's where it would stop. So should equal 4 PC, and should equal, okay, we're going to add 1 to the accumulator, jump over that one, so the accumulator should be 1. Now it's going to fail at that, obviously, right? Good. Okay, so now we need to execute this. That's going to be really interesting, isn't it? Okay. So we're going to start with a machine, and instead of doing that as a let, let's make this a loop. I'm going to do this as a recursive algorithm. Let's just see what happens. So the machine is going to be, so we loop with the beginning machine being AC0, PC0. That's how the machine will begin. And I already have the program, so I don't need that. I think that's everything for the moment. There is something else I want to accumulate, but I'm not going to do it yet. And that would be the history of the execution, but I'm not going to do that yet. Let's get the execution working first. All right, so now I want to get the instruction at the program counter. So let the instruction be the get machine get program there. I think that's correct. I could have said nth get. I think get works. Just looking here. So that's going to be the instruction. Then we're going to say, and what is the instruction? The instruction is going to be, let's destructure it. The opcode and the argument. Okay, so every instruction has an opcode and an argument, and we're going to get the instruction. Good, okay. The little clever thing I was thinking I would do here was turn that into a function, but I don't think I'm going to do that. Okay, now it should be kind of obvious that what we're going to do next. And there's the get, right? What is, oh, yeah, get rid of that brace there. Okay. So now the next thing we're going to do, now that we have the opcode and the argument, is that we're going to do a cond p equals opcode. And this is going to be really simple. No op, yeah, and there we don't even pass the argument. Jump, jump. Ooh, but I do need to pass the machine. Jump is going to be the arg in the machine. And ACC is going to be the, oh, that's interesting, the ACC of the arg in the machine. Yes, okay, good. And now what should happen if we don't execute any of these? And the answer to that will be halt. Which I'm not going to even execute, right? There's no instruction for this. So the answer is just going to be the machine. Okay. Now, is that going to stop execution? No, it's not going to stop execution. So, next thing we need to do is up here, if, and by the way, I neglected this, you know, the very first thing you are supposed to write in a recursive algorithm is the termination clause. So, Bob, remember to do that. So if the PC, all right, so if, and it's going to have something to do with the PC, and if that is greater than the size of the program, okay, or equal to, because it's zero indexed, right? So if it's greater than or equal to the count of the program, then we're done, right? Then this is done. So we're just going to return the machine. And we're done. Okay, now these here, they're not quite right. Yes, we are going to do the no ops of the machine and so on and so on. Yes, that we are definitely going to do, but we're also going to continue the execution. So this is going to be a recur of the machine returned by the no op instruction. This is going to be and I don't need to do it that way, do I? Because I could do it here. Gee, that doesn't look really good, does it? Let's see. Return, recur, And then we're going to do the cond p. That's going to be correct. And it seems to not have the right parentheses here. Good. All right. Yes. Oh, no, that's not right either. That one goes there. Good. Okay. And then we have the recur and the let and the if and the loop. And then we need that. Okay. And I think that is correct. So if the PC is greater than or equal to the size of the program, then we're done. Otherwise, we are going to get the opcode and the argument from the PC, from the instruction at the PC, and then we're going to execute again with the machine returned by either the no-op or the jump or the ACC instruction. Now let's see what happens when we run that. Oh, heavens! Oh, heavens, man. Apparently I know how to write code. Okay. The next thing we need to be able to do is stop if we have re-executed an instruction. All right, and for that, I want to accumulate the history. So I want to change the execution program to keep a history. Now, where do we keep that history? Well, we could keep it in the machine. Like right there. We're going to keep it right there. So that will be actually in the machine. The machine will have a history argument. Why not? Okay. Now, what should that history argument be? Well, it should equal the list of instructions executed, which will be 0, 1. So this is 0 here. This is 1, 2, and 3. But that's it. 0, 1, and 3. That should be the history. Should equal 0, 1, 3 history. Now, that is not going to work at the moment. It's going to return a nil because there is no history. So now let's do the history. And we do that by saying that the history is the empty list. At this point, this should now have changed to, well, it still says nil. It's because my recur function should return some kind of a list. Right? Ah, heavens! Let's see, what did I do wrong here? Mismatched argument to recur. Expected one argument got 2. Wait a minute. Why is it? Oh, yes. Okay, sorry. So now the cond p is returning the new machine, but without the history. Now, we could put the history into the instructions, but it's really kind of an artifact of execution, isn't it? So what we're going to do is we're going to pull that recur out of there and out of there. And we're going to replace it with a let new machine be the cond p of the old machine. Yes, okay. So that would go like so, and then there needs to be another parenthesis to close the let. Good. All right, and now we've got the new machine. Okay, but these functions here do not record the history. So let's get the history. So when we execute, we're going to want to save that history, which we've got. Okay, we've got the history. All right. So we have saved the history. Have we? No, we have not saved the history. That's only the first time through. So machine, here, I'm going to do this. So I'm going to save the history because I know I'm going to need it later. All right, now I think I've got this all done correctly. So this is a oh wait. Do I need the second let in there? Probably I don't. So let's take that out. Let's see if that works. Whew. Okay. I'm getting the history out here. Should I get it out of? Should I get it out in here? Let's get it out in there. Yeah, because we don't need all this indenting, right? So let's pull that out. Yeah, I know. Okay. Yeah, new machine is going to be equal to the cont p. Good. Okay, but before we do that, let's also say that history equals the history of the machine. Okay. And then the new machine is going to be the cont p of all this stuff. And can we join that? Is that, reasonable to do? Well, sort of, I guess. All right. And now we need to return the new history. Okay. And the new history, let's get the PC out of the machine. Okay. All right, so now we've got the new machine, the old PC and the old history. Okay. And we're going to say return update new machine history, you dog, history conj PC. Whew, okay, I got a bunch of things wrong here. There's a let, there's the if, there's the loop, there's the def, and that one goes away. Let's see if this lines up properly. Something went wrong with the history, but maybe that's okay. Let's make this as an assoc. New machine, history, conj history PC. Now, this is probably not going to work. just to let you know, it's probably not going to work. Expected a 4 got a 1. Boy, I didn't expect that to fail. So, let's see, which one failed? What failed here? Should execute a jump. Well, should execute a jump seemed to work, but most of the other ones kind of gave me a problem. Execution should execute. Expected a 4. So the PC didn't get updated correctly here. Why not? Okay, so I got the machine. The machine is here. And that's just... Oh, what did I do with the recur? Yeah, okay, Bob, got to do the recur. Recur. The machine, the new machine. Okay, that's, you know what? Let's do this. Let's say this with new machine. Yeah, okay, so new machine is the assoc. Let's just do that because that's just an awful lot of crud, isn't it? Yeah, okay, and then we say recur new machine. There's the recur. So, and that's still inside the loop, and everybody should be happy with this. So, let's just save it and see what happens now. Ooh, everything worked. Once again, Uncle Bob knows how to write code, sort of. I can't say I'm very happy with this, but it does seem to work. Okay, so now it's recording the history, and that's good. Now it should exit if it should exit if an instruction is going to be re-executed, which means that if execute finds that the current PC is in the history, it should execute immediately. Okay, all right. So let's do that test. Okay, it should halt when asked to repeat an instruction. Okay. That's going to be a different program. So let the program be. Well, this is going to be pretty straightforward. Let's just say no op 0, and then jump -1. That should halt. And let's just add a no op here so that we know that it does not get that far. All right, that is the let. Good, got that. Now, let the, no, that's not what I want. Let the final, the machine be the execute of the program. I think that's the way that goes. Yeah, okay. Let the machine be the execute of the program. Good. Now we're going to do the shoulds. Should equal, and the PC should be 0. Let's do this. Let's turn this into an ACC of 1. All right. To make sure that we do execute that. Okay. So should be 0 of the PC of the machine. Right? So it's tried to execute that accumulate more than once. And should equal 1 the AC of the machine, because it did execute that once. Now, this is going to fail horribly. He said. I think it's executing an infinite loop. Which is exactly right. It's executing an infinite loop. So stop that, Bob. Okay. We don't want it to execute an infinite loop. So we need to stop it. And we're going to stop it in this if statement. Or. Okay, now we want to know if the PC is in the list. And that means we just want to find something in a list. I think there's some function that does that. There's a contains function. Yes, okay. Or contains colon history. History of the machine, the current PC. And contains has a question mark after it. I think that's all there is to it. Let's see if this runs. Oh heavens, look at that. It worked. It worked. Okay. Well, if that worked, let's write an acceptance test, shall we? All right. So that's the end of the describe. That's good. Let's just put a nice little blank line there. Let's join those lines. Let's join these lines. Clean up just a little bit of cruft. Okay. Let's write ourselves an acceptance test. Acceptance tests. Okay. It should pass the first acceptance test, which was given to us in the day of code. So let us find out. Oh, heavens, we haven't done the parsing. Not time for the acceptance testing yet. Let's do the parsing. All right, so describe the parsing. Okay, it should parse one instruction. Okay, well that should be easy. Should equal. Let's see. Jump 1. Jump 1. Yep, that's it. That's the way that's going to go. That should be parse instruction, right? Okay, because that's the way these appear. They have plus and minus signs, but I don't care about the plus and minus signs. Well, I do care about the minus signs, obviously. Okay, well, that's probably going to fail because I don't have a parse. So let's make the parse. It's actually a string. Let's just call it S. Okay, got it. That should fail some horribly because it got a nil. Okay, so first thing we're going to do is parse it out. So let opcode and arg yeah, you're going to know why I'm doing that in a minute. Be the RE matches. So this is the regular expression matcher. And here's the regular expression. Yeah, oh, no. Yes, okay. So this is going to be 3 letters, right? Now, alphabetic letters are what? Yeah, this is going to be a pain in the butt. I could just say dot, 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 because it's anything, right? But let's take a look at the patterns. Just, we're going to look at the Java regular expression patterns. And let's see. Yeah, I know what to do here. I knew all along what to do here. A to Z of 3. So every opcode is 3 characters, A to Z. But we want to be able to capture that. I don't know what that closing brace is there. So we want to capture that. So that's going to be put into a capturing group. That's what the parentheses mean. This is followed by a space. Then it's followed by a possible, and here we're going to do a capture group. Okay, it's a possible plus minus, And oh, by the way, this is A to Z. Oh, lordy. That's going to be a backslash, and that's going to be a backslash there because those are both special characters. And that's going to be a 0 or a 1. So it might contain that. Followed by, so I need to make that an optional thing. There's some way to do that, which is it's not star and it's not plus. It's 1 or 0. So that's like 0 to 1, like so, followed by some numbers. And the numbers are going to be %d plus, and then after that, nothing. Now, that's the regular expression. Okay, and S. Yes, that's the string that we're going to parse. Okay, fine, and let's just return that and see what it does, huh? Because that's an awful lot of junk. So return underscore. Here, let's do this. The match. So return the match and the opcode and the args. Let's just see, what it actually gets from this, if anything. And what did we get? We got a nil, nil, nil. I expected a jump 1, but I got a nil, nil, nil. Yeah, okay, fine. So something was wrong inside this regular expression. It should have gotten the A to Z. Oh, well, sometimes they want a dot star on the end. Ooh, heaven, that didn't change a thing. Okay. Let's start easier than this. Let's just say that we want that. Does that much work? Oh, heavens. That did seem to like something. We got the jump. We did get the jump. Okay. Well, that's good. All right, so since we got the jump, what we need then is something better than that. And by the way, this is supposed to be a plus or a minus. Looks to me like, let's take a look at the input. Those signs are there. Okay, those signs are definitely there. So we're going to assume that there will be a plus or a minus sign. It was nice of them to do that for us. So, okay. So then the next thing we're going to see is going to be the capture group, which has a sign in it. And that sign is going to be a dot. I don't care that it's a plus or minus. Doesn't matter. But I know it's going to be there. Oh, and I need the space. Let's see. Is there a space there? Yeah, there's the space. Okay. All right. Then I'm going to get a dot. And after the dot, it's going to be %d plus. Now, my feeling is that should work, but it didn't. And it broke everything. Right? So nothing matched, which I find odd. Let's take that dot star off the back end and see if that matches anything. It does not. Okay, isn't it %d? Isn't it %d for digit? Isn't a digit a %d? Let's see now. Oh, it's a backslash d. Bob. Backslash d. Okay. Oh, look at that. Okay, that's good. All of this is good. Okay, so it did in fact get the jump and the +1. That's good. All right, so now what I want to do is change it to a number and an opcode. Well, I don't need that M anymore. The arg is going to be integer / parse int. of the arg. And that's capital integer. Okay, and if I check that, it should now say, oh yeah, look, it's got an integer there now. Okay, and the opcode should be keyword, is it? Can you do that? Keyword. Keyword, can you do that? I've never tried that before. It might work. Leave me alone, leave me alone. Oh, look at that, all worked. Wow, okay. By the way, that means they'll all work. So now I can parse one instruction. All right, so then I just want to parse a bunch of instructions. Let's see. Where's the int? That's dirt trivial, right? So it should parse many instructions. You bastard. I hate the new touchpad on my laptop is awful. Awful. It's big. My palms touch it. Every once in a while I put enough pressure on it to make it click and it makes me crazy. All right. It should parse many instructions. Good. Okay, Bob. All right. So, should equal, okay, colon jump 1, colon nop 4. Okay. And that's going to be parse instructions of jump plus 1 backslash n nop plus 4 backslash n. And let's make that so we don't overflow. All right, parse instructions. Yeah, you know, the S is kind of a bizarre thing to do there. Let's just rename that as instruction. And let's rename this as instruction. I know that makes it bigger, but you know. Here, let's do that. That's better. Okay. Okay. So now we're going to, this is really simple because this is just Clojure string slash split instructions by the regular expression backslash n. I think that's all it is. Let's see, expected jump with got. Oh, yes. Map parse instruction over the splitting of the, yes, all right, good. Everything works, lovely. Heavens. Okay, now it's time for the acceptance test. Now, okay. Describe the acceptance tests. Okay, and the very first one is it should pass first acceptance tests. Right, this is the acceptance test for problem 1. And they give us this lovely example, which is this. I'll show it to you in just a second. Okay. Okay. Let the input be a string containing all of that junk. Okay, that's their test. And let's see. Yes, I know I could reformat that, but why would I? Should equal. And they say that here the value in the accumulator is 5. So the expected value in the accumulator should be 5. So this should be the AC of the execute of the parse instructions of the input. What do you think, guys? Oh, heavens. Got 0. Okay. We got our input, and it should have parsed it properly. It looks to me like it's perfectly all right. So let's actually break this up so that we're not doing this massive should. Okay. And let's put a \n on the end of that, just because I don't trust things if they don't have line ends. Okay, and then I don't want that closing brace there. So now, the instructions are going to be the parse instructions of the input. And let's just print that. Just to see what we get. And okay, we got a null. What did it print? Didn't print anything. Let's see. Is everything normal here? Yes. Did we execute? No. Oh, I'm not real bright here, am I? Print one. There we go. Okay. Oh, goody, 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 goody. And what did we print? We printed nothing. Didn't print anything. Why didn't we print anything? Number format exception. I never did try a negative number here, so let's try this. Let's make that negative. And this should be a jump -1. Let's see if that passes. So that's one of the parsing tests. Yeah, it's passing all that, so it's really this acceptance test. And it's just got a null. Maybe it doesn't like the fact that I don't have a should. Okay, so there's a dumb should right there. Now, let's see what happens. Now, that was no difference at all. Acceptance test should pass first acceptance test. Yes, that's the it. Right, so I've got a describe, and I've got an it, and then I've got a let. And that's fine, and the let should work just okay. It should print the instructions, but it's not. And let's make sure the parentheses are right. They are. Okay, so there's some number format exception that we're bumping into. Where? Where? Well, okay, so let's do this. Let's println input here. Let's see if that even prints. You know, I keep on trying to hit these characters and they don't want to hit. So, all right, now let's see what happens. Yes, okay. So that part did work. So the number format exception is occurring somewhere else. Wonder where. Now here it says 31. I don't believe that because that's up here. Oh no, it's over here. 31. 31. Yes, silly me. It's doing, yeah, it's blowing up on the parseInt. I wonder why it would blow up on the parseInt and what it's blowing up on. Okay, so let's do this. That'll tell us probably which instruction it's blowing up on. Well, it seems to think that's fine. try it that way. Ooh, that's interesting. What's going on here? How come we only see... Wait a minute. What? Something weird happened here. Parse instructions, Bob. Dumb. Okay. Expected 0 got 1. I don't know where that was. I don't know why it's a 1 either. But okay, let's see. We did parse it. We did get it. Did we get it all? Yes. And the minuses work, and everything seems to work fine. Okay, good. I can get rid of all these dumb print statements now. I'll probably have to just put them back in a minute, but all right. Run that test. Lovely. Unmatched delimiters somewhere. Damn it. Oh yeah, I've got the brace there. All right, good. Okay. Everything passed except the first acceptance test where we expected a 0 but got a 1. Oh yeah, and that's because, yes, okay. So all that apparently is working fine. So now what we want to do is should equal, and we'll put our regular thing back in there, which was the accumulator should equal, what was it, 7? 5. 5, that's what our acceptance test said. The accumulator of the execute of the instructions. Ooh, okay. Expected 5 got 0. Now, that's interesting. The execute does begin with a history of nothing. Right, so that should be fine. So let's do this. Let's trace the program. We should be able to do that. We should be able to trace this program by reaching in here and doing a print of and let's get the PC and let's get the opcode and the arg. Just print all of that and see what happens here. Seems to me we got a 0 and a null and a null. Okay, I'm doing something stupid here. Something stupid I'm doing. I'm not exactly sure what. But something stupid is happening here because I'm getting a 0 and a nil and a nil in my very first instruction. Right? Because the other ones seem to work just fine, right? So those worked okay. So a 0 and a nil and a nil. Huh. Okay. If I print those instructions, okay, no up 0, ACK1, jump 4, ACK3, jump -3, ACK -99, ACK1, jump -4, accumulate 6. Yep, that's the right program. Absolutely the right program. Okay, I should be able to execute that program. Executing the program, yep. Okay. Okay, yes, I know. I'm being silliness here, but I just want to check everything. Yes, I'm executing the right program. Yeah, executing the right program. Still got a 0, 0, 0. So I'm doing something stupid. I'm not exactly sure what the stupid thing I'm doing is. Execute returns the end state of the machine. I should be able to get the AC. It says it's a 0. Execute. Execute returns the end state of the machine, right? Right? Yes, it returns the end state of the machine. It's not executing anything anyway, right? So where's that 0, 0, 0? Right there, right? It's getting a 0 and a 0 and a 0 right there. Why? Why is it getting that? Is the get failing? Okay, so I think I figured this out. And this is one of these weird things about Clojure. This get function here works on a vector. Doesn't always work on a list. Right? So if I print okay, I can type. This new keyboard is really bothering me. If I print the get of the program 0, that would be the PC at 0, right? The first instruction. I'm going to print that, and then I'm going to print the program, just so that you can see, right? And if we run this, what you see here is a nil, right? And here's the program. And you see that the program is a collection of a bunch of lists, but it got a nil back. So get doesn't seem to want to work on this here. Now, it did work in the past. The reason it worked in the past is that I was passing in vectors. So if I change this to a vector, if I change the program to a vector, I believe it will work. So, okay, apply vector. So I'm going to apply the vector function to the program. Okay, and that's fine. And then I'm going to just get that. So I'm going to get from the vector the 0th element. And now when I do that, you see, oh yeah, I got that no op down there. So that, I think, is the problem. Okay, if that is the problem, I should be able to fix that in my parsing. When I parse it, the where is my parsing here? Oh, parse instructions, which does a map. It creates a map of everything, and then that map I'm going to turn into a vector. Oh, isn't there like a map V? There is a map V. Okay. Well, okay. Now, okay. Well, that's clearly different from before. Expected 5 got 2. So something is happening in there, different from before. Now let's print those instructions out and see what it's doing. So let's see. Right in here, we will print line. Let's do this. The opcode and the arg and the PC. And let's print the PC first because that's kind of traditional. Colon PC of the machine. Good. And the opcode and the arg. Okay, good. And what do we see? Well, we see that it executed the no op and then the accumulate and the jump 4 and ACK1 and then jump -4. Now, if we look at the actual program, does that make sense? Well, okay. So we executed the no op here. That's the no op. Good. And we executed the ACK1. That's good. And then we executed jump 4. Well, okay. 1, 2, 3, 4. That's going to be an ACK1. at location 6. And then there's a jump minus 4. 1, 2, 3, 4, where we've got, well, that's where it stops. So why do they think the accumulator should be 5 here? Yep, jump 4 sets the next instruction. So I'm looking at their analysis now. And I'm going to look at their program. In fact, let me bring it over for you so that we can look at their program and make sure that their program actually makes sense. All right, so I'm going to bring this over here. This is the program. And so let's just execute it in our heads. Okay, the accumulator is a 0. The accumulator is a 1. The accumulator is a 1. We're going to jump plus 4. 1, 2, 3, 4. The accumulator is a 2. Jump minus 4. 1, 2, 3, 4. Ooh. I think that jump minus went wrong, didn't it? Because when I did it, it executed something that had been executed before. It stopped there, right? But here it didn't. 1, 2, 3, 4. So is it possible that I am adding the R? Oh. Wait a minute. My jump instruction. PC plus arg. There's the jump instruction. PC plus arg. So if the PC, so here I am at jump minus 4. That should take me back to 1, 6, 5, 4, 3. It should take me back to 3. Now, instruction 3, 0, 1, 2, 3 is the accumulate plus 3. But that's not where it went to. Where did it go? So that's interesting. It seemed to stop there, which means it found something in the history. Well, okay, let's go take a look at our history. Let's print the history here. We should be able to do that. So here's our print. Here's our history, right? Good. History. Let's just print that. All right, now let's see where we are. Nope, can't seem to do that. Yeah, okay, fine. Ah. Okay, here we go. 0, 1, 2, 6. Okay, so all of this looks fine, right? By the time we get to 1, 0 is in our history. By the time we get to 2, 0 and 1 are in the history. By the time we get to 6, 0, 1 and 2 are in our history. By the time we get to 7, 0, 1, 2, and 6 are in our history, and then it stopped. Now, why did it stop? Okay, he said, well, let's put a print statement up here. Okay, we're going to print the machine there. Okay, so the last executing statement, the accumulator was 2 and the PC was 3. Now, was the PC supposed to be 3? 7 is in our history. Right? So was the PC supposed to be 3? Well, okay. We got down to this jump minus 4. Okay, 1, 2, 3, 4. Yes, that is location 3. So why did it stop? What would have made it stop now? Well, okay. Does the history contain a 3? And the answer is no. All right. Why did it stop? Should not have stopped. Or is the PC of the machine greater than the count of the program? Well, no. So why did it stop? Let's print here the instruction that it's about to execute. I think it's going to be the right instruction. Get program :PC machine. Now, I believe that's going to print the... damn it. Yep, okay, good. Yeah, Act3. That's the right... yeah, that's right. Okay. So, but it stopped. Why did it stop? So now we got to figure out why it's stopping. Well, yikes. Yikes. Okay. Is it possible that contains... well, there's only one way to do this, all right, which is going to be a pain in the ass, but all right, fine. Here, let's do a let. Too far is going to be this one. And re-execute is going to be this one. Okay. So it was re-execute. So it's, I said contains, and I gave it a history, and the history is very clearly right there. And the PC is very clearly right there. And it said, hey, does that contain it? So the contains function may not work the way we think it does. Let's go to a REPL, which, you know, see, how did I write that? Contains the list and then the 3. Okay. Well, that's interesting, isn't it? Contains is not quite the right thing. What is contains? Let's see. Returns true if the key is present in the given collection, otherwise returns false. Note that for numerically indexed collections like vectors and Java arrays, this tests if the numeric key is within the range of the indexes. Oh, well, that's not useful, is it? All right, so contains is not exactly what I wanted. I want to be able to find an element in a list. Find element in list. I could convert it into a set and do a membership test. Contains is the wrong thing. It is not contains, so let's get rid of this whole let thing here. Yikes. Okay, and for some reason my test passed when it shouldn't have, right? But the condition was just right for the test to pass without this being probably right. So I'm going to turn it into a set. I think you can do that. Oh God, now it passes. All right. Well, that was a little bit disappointing. Okay, so if I turn the history into a set, then it will contain it. Okay, fine. All right. Well, now we should be able to solve the problem. And if we, yeah, fine, go there, do this. Okay, so right now we want to read the input file and find out what the number is for the whole input file. So here we go. We're going to describe the solutions. And it solves one. Okay, to do that, what we're going to do is we're going to say let the input be the slurp of input. That's our input data. All right, then we are going to make our program. Okay. Then we're going to get the machine after executing. And let's just print the machine. Okay. 1810 it says. That's supposed to be the execution. Look at it, printed all this stuff. Oh, man. Really did execute for a good long time, didn't it? I still have my println in there. Let's get that println out of there. We don't want all that junk being printed. Here, let's run it again. Okay, now it's not printing a bunch of junk anymore. Still 1810. Let's go here and answer it with 1810. Okay, let's see if that worked. Yes, that's the right answer. Okay, all right. God, what a terrible problem. So let's do one last thing here. Let's clean this up just a little bit. This bit of code right here could probably go into a new function which just executes one instruction. And let's see, what does it need? It needs the machine. It needs the program. And I think that's all it needs. So let's just do this. Okay, we're going to say execute instruction. And we'll give it the machine, and we'll give it the program. All right, and that's pretty straightforward. I think it's just going to be defn execute instruction. Don't you wish we had a an extract method? Machine and instruction. Okay, and I think I can just paste that. A little bit of a thing here. Let's see. Did I just do this wrong? Was the machine in the program? Right, program, yeah. All right, machine in the program, right, and well, let's just try it, shall we? Oh, heavens, something broke terribly. Mismatched arguments to recur. Let's see, I probably broke it right in there. Ooh! Well, I can't really call recur, can I? So what I really want to do is call recur based on the new machine. So recur there. not here. Okay. And that gave me my 1810 again. That's nice. So it's just a little bit nicer, managed to do one extract method, extract till you drop. I'm not sure it's worth extracting anything else. I suppose I could extract that. I don't know if it's worth doing that though. So, yep, let's just leave it the way it is. And for our final act, we will say that this should be 1810, and everything passes. Everything passes. All right. I think we've had enough of this.